Welcome. Today's notes worksheet is entitled Constructing Functions. We'll go ahead and develop a few strategies for the ideas that we're going to see in this particular section. And then I have 4 examples on this notes worksheet. And hopefully after the 4th example, you'll be able to transition and try some of these problems on your own. Well, why don't we go ahead and start with the 4 strategies that I have listed on your sheet here. And I'll go ahead and just read them and highlight anything that I see that's important. And then we'll dive right into example 1. So first one right up here says draw a labeled diagram if necessary. I've always said I'm a very visual person, and so when I read a problem, it helps when I see something that I can label, and then the mathematics comes from there. So number 1, always draw. Be visual with it. Number 2, write any information you can into a mathematical equation. Typically, you'll be able to write 2 equations. Not always, but you'll see some of the information in the problem lends itself to writing 2 different mathematical equations. And then 2 and 3 go hand in hand here, everybody. What we're going to want to do is use substitution in order to write a function in terms of a single variable. In fact, that is our purpose of the lesson. That is the objective right here. So write a function in terms of a single variable. That's great. So as a matter of fact, because 2 and 3 kind of tie together there, and they are probably the primary objective, let's go ahead and highlight that piece. And then number 4, what we're going to do is just try to manipulate the function a little bit, so simplify it and utilize it according to the problem. So there might be a second tier after we write our function that we might want to deal with, and we'll go ahead and see what that might mean over the course of the 4 examples. Well, why don't we go ahead and get right into example 1. I'll go ahead and read it off here. And by the way, I believe this one is a rather easy one. It kind of starts off, and then we'll hopefully build up from there. So example 1. The volume of a right circular cone is V equals 1/3 pi r squared h. If the height is twice the radius, express the volume V as a function of the radius r, then determine the volume of the cone if the radius is 6 inches. Perfect. So right away what I'd have us do, and I'd encourage you to do this as you work independently, is really highlight what the objective is. And so what we're trying to do is express the volume as a function of the radius. So underline that piece right there. That's the function that we're going to construct. Volume will be our output. Radius will be our input. And here's what I do, and you can do this or not. It's totally your call. But as soon as I get the idea of what is in the problem, in this case volume as a function of radius, I actually go ahead to my answer space and I write the notation that will produce that. Volume in terms of radius, V of r. So I kind of just get that together and sort of get me thinking in the right direction of what I'm looking for. Then I go back to the information in the problem. So in this one, I'm not going to bother with the label diagram. I definitely will on the next 3 examples. I think in this case, if you want to go ahead and draw a right circular cone, that's perfectly fine. But I think we've got enough information to work with that we don't need it. So anyway, what I see here, again, the objective, volume in terms of radius. And if I have to write a function for volume in terms of radius, I think it benefits us to just try to write any mathematical equation dealing with the volume of the cone. And it just so happens in this one, what makes this maybe easier than the other ones that we'll see, is we actually have something along those lines. We have volume, in this case in terms of the radius and the height. So I'm going to go ahead and rewrite that piece right there. So 1/3 pi r squared h. And that's great. I mean, that's exactly what we want in terms of starting it out. Remember the goal, volume in terms of radius. Right now we have volumes in terms of radius, but also in terms of the height. And here's what I'm going to ask you to do, and I do this all the time. H is the issue. We don't want h in our equation because we only want it in terms of a single variable, and our single variable, of course, is r here. So the h is the dilemma. We've got to eliminate the dilemma. So circle that piece if you would, and the question is how can we replace that h in the equation? So what I'd ask us to do is go back to the example. And what we need to do is write a second equation. As it says, and this doesn't happen all the time, guys, but essentially it says write any information you can into a mathematical equation. Typically, you'll be able to write 2 equations. Well, we wrote 1. That's beautiful. Now what I need is a second one. And so if you kind of look at the problem here, what we're looking for is a relationship between height and radius, and I think I have that right here. Height is twice the radius. And so what that allows me to do is to write a secondary equation, and I'm going to do it right next to it. Height is means equals. Twice the radius just means 2 times the radius, and so h equals 2r right there. So all I did is translate this piece of the problem into a mathematical sentence. Perfect. Now you'll hear me talk a lot about this over the course of the 4 problems that we do together, but the bottom line here is if I need to replace the h, then I need to solve for h in a secondary equation. And if you notice, it's already solved for. H is equivalent to 2r. So what I do, and again it's up to you if you want to follow my lead here, but I circle what h is equivalent to, and not to be too dramatic about it, but I go ahead and draw a little arrow going in, and that 2r is going to of course replace the h in our volume equation. So that goes in, everybody, and then I've got v equals 1/3 times the pi times the r squared, and obviously instead of h, it's times the 2r. Now perfect, I'd ask us to try to simplify things. There's just some good algebra in this. So I'm going to play around with this a little bit, but in essence I've done my job here, everybody. I've got volume in terms of just the radius. That's it. And that's what I was looking for right here. Volume in terms of just the radius. Perfect. Again, as I said, I'm going to play around with this a little bit here. It's all multiplication as a matter of fact. So 1/3 times pi times r squared times 2 times r. I can change the order on that, just make it a little more visual and a little more user-friendly. So I just see the 2 times the 1/3 times the pi there. I'm going to lay that out like that. And then the variables times the r squared times the r. And I have a feeling you could probably play around with this and simplify it yourself. I'm going to go ahead and get that going right here. 2 times 1/3 should give us the 2/3. So 2/3 pi is our constant in this case. And then r squared times r, of course, would be r cubed. So simplify, and that's what number 4 said. Simplify the function if you can, and I'd encourage you to do that as best as you're able. Okay, this looks great. Volume in terms of radius. And so now it's ready to go. It's simplified. Let's just put it in the answer slot. So 2/3 pi r cubed. Now the idea would be I should be able to utilize it in any way that the problem asks. And as you can see, if you read the problem, there is just a secondary piece. So it says, then determine the volume of the cone if the radius is 6 inches. So we're given an input. Radius is 6 inches. And we're just going to come up with the output. Good function notation here, everybody. So I'd encourage you to do it exactly like this. We're looking for a radius of 6, so v of 6. And so given any input, you should be able to come up with the output. And so I'm looking for 2/3 times pi times 6 cubed. And we could probably get an exact value on this. I think I'll forego that, though, and go ahead and get just a decimal approximation. So I'll grab my calculator. If you guys can do the same, that would be ideal. And let's see what we've got going on here. So 2/3 pi and times the 6 cubed. So we can just rush this calculation right here. Here's my 2/3 pi, and then times 6 cubed. That should do it. And you see we get about 452 and change. Sounds great. I'm going to go ahead and write that answer down just right in here, and then in the answer spot, potentially with some units behind it. But I've got about 452.39, and that's looking nice. As mentioned, given any input, you should be able to come up with the outputs. Given any output, you should be able to come up with the input, and not too bad at all. So let's see, that was 452, roughly 0.39, and I think we were in inches in this case. Yep, there we go. And so our volume would be cubic inches. Excellent. So just a nice way to ease into the fact that we've got 2 equations, and we use substitution to write one equation in terms of a single variable, v in terms of r. Let's go get example 2. Now example 2 is just a slightly obscure one, but I like it. I think it's got a lot of merit to it. It's very visual, it's got multiple parts, and there's some good algebra along the way as well. So let's go ahead and try example 2 here. I'll go ahead and read it, and I'll help you with the graph, and so when you do one similar to this, you'll have an idea of what to look for. So here we go. We've got a point xy, so just an ordered pair essentially, is a point on the graph of y equals the square root of x. Express the distance d from that point to the point 1, 0 as a function of x. Then determine the minimum distance between the 2 points. Finally, determine the coordinates of the point on the graph of the function that will produce the minimum distance. Okay, perfect. So let's start off with some of the basics here. Let's see what the primary objective is. We're going to construct a function, of course, as the title of the notes does suggest. And so it says express the distance d, so output is d, from the point to that point right there as a function of x. All right, so underline that piece for me, excuse me. So it looks like we want a function d in terms of x. Everyone see that? D in terms of x. Well, that's super. I'm going to go ahead and get this notation going just so I know what I'm looking for here. I think that's it, d in terms of x. All right. Well, how this is going to play out might take a little time to develop, but let's see what we can do. So on your paper, it does say graph. And if you would, you can just give me a coordinate plane just looking like that. That should suffice. Shouldn't be too big of a deal. And so what we have here is a point on the graph of y equals square root of x. So let's just focus on that first sentence right there. So we've got a point on the graph of y equals square root of x. Well, everyone, let's go ahead and draw y equals square root of x. We should sort of remember what this function looks like. That's not perfect by any means, but it should suffice. So this is y equals square root of x. I'm going to label that. Again, just the more things you label, the more it's like to stimulate an idea or two as you go ahead and try to construct and utilize these functions. So there we go. Y equals square root of x. That's great. And it does say there's a point on the graph of it. So I'm just going to pick any point. It's not a fixed point. So there is my point, x comma y. Beautiful. And as a matter of fact, just as we label these, this is what is called a variable point. Obviously, it can move up and down the graph of the function. So that is my variable point right there. Excellent. Okay. And we're looking for the distance between that point, so from our variable point to a particular point on the coordinate plane, 1, 0. So, all right, it tells us where to go. So from that point to 1, 0. So everyone find 1, 0 there if you would. I'm going to go ahead and label that piece right in there. And by the way, that was what we would call a fixed point on the graph of the function, or not on the graph of the function, just on the coordinate plane. All right, nice. So we're looking for this point, which will of course slide up and down the graph of the function to this point right here. So we want the distance between the two. I think it is time to go ahead and throw that distance in place. If you guys want to go ahead and label that d, that might not be such a bad idea. And that's it. And you notice, obviously, as this point moves, the distance will change. And so the distance is dependent, obviously, on this point, but more specific, this distance is going to be dependent on the x value of that point. And that's what we're looking for, distance in terms of x. All right, well, let's go ahead and play around with it. Well, the first order of business, I guess, is to talk about the distance between 2 points on the coordinate plane. And so this kind of goes back to maybe Algebra 1-ish, but let's see if you remember. It would be great if you could stop for just a second and see if you can go ahead and write the distance formula down. See if you remember it. It's the one with the big square root. Well, I recall distance formula as something along these lines right here. And it's just a variation of the Pythagorean theorem, as a matter of fact. So we've got our x2 minus x1 squared plus y2 minus y1 squared, all underneath the root there. And so that's the distance between any 2 points on the coordinate plane. That looks great. Obviously, we need to get quite a bit more specific with this because we want distance in terms of our x value right here. Well, if I asked you to come up with the distance between these 2 points, x2 minus x1 squared, y2 minus y1 squared, and that should be thrown into this formula right here. So I'm not ready to write this as a function just yet, but I am ready to move forward with it. So let's do exactly that, everybody. Distance between these 2 points, one more time, x2 minus x1 squared, so x minus 1 squared, and then plus, and then it looks like y2 minus y1, and then squared. So of course, y minus 0, and then squared. Theoretically, the order doesn't matter. I think this is actually probably the cleanest approach, though. And that looks great. Now we've really started to narrow it down. I want distance in terms of x. I've got the good and the bad in my problem right now. I've got distance in terms of x, but I also have it in terms of y. So remember, there's that little dilemma right there. I don't want y, so circle the y. And so what we need to do in this particular case is find a way to get rid of that y. So look at your paper for just a minute, and can you write a secondary equation from what you see that will allow us to substitute in for that y? And I'm hoping that you see this piece right here. We know y in terms of x, right? Y is equal to the square root of x. So as a matter of fact, I think we're pretty much ready to go. So this is what y is equivalent to. Everybody circle that. Again, not to get too dramatic about it, but draw the arrow right on in if you would. And so that's going to replace the y right there. When it does, will I have the distance all in terms of x? Absolutely. So let's see what we want to do with this. I'm hoping you can see a couple things that simplify. We don't have to do too much with this. But let's see, we've got, and then this piece, square root of x minus 0, and then squared. And again, theoretically, we've done our job here. This looks great. I might clean up a little bit. This one's over here is kind of begging to be simplified. Square root of x minus 0, I'm hoping you would agree is just square root of x. And then what happens when I do square root of x squared? Well, in that particular case, the square root and the square would cancel. So I'm going to take this in 2 steps just in case you didn't get that as I said it there. So x minus 1, and then square root of x minus 0 is just square root of x. And then here was what I was thinking of right there. Just those 2 things cancel out. So I'm seeing this. Hey, theoretically, could we FOIL x minus 1 times x minus 1 and then maybe combine a like term with that x right there? Probably. I don't know. I don't see it's truly necessary. I kind of like this. I think that's really nice. Distance in terms of x. It's ready to go. So I've got x minus 1 squared plus x. That's looking great. Now, as mentioned before, you can kind of see that the distance obviously is going to change depending on our x-coordinate. You know, if I probably come out here, pretty large distance. If I come in here, smaller distance. Now, just to expedite this along, there happens to be a distance somewhere right in here, probably, give or take, that's the smallest, that's the minimum. So this is what is called optimization. And what we're going to do is optimize our function, in this case minimize the function, and figure out the values. Okay, well let's go ahead and do it. So anytime we optimize, and by the way the optimization will come from either maximizing or minimizing, we want to go ahead and graph it on the calculator and then come up with a max or a min. Okay, well let's get it in. Grab that calculator if you would. I'm going to do x minus 1 and then squared, and then plus the x. And that's our function right there, looking pretty good. Now the window is going to be the hardest thing when you guys optimize. I will help as best as I can here. It's somewhat of a cop-out for me to say it, but in some respects it's a little trial and error. If you have some good number sense with these functions, you can probably find a good window pretty quickly. If it takes a while, again, just let me know and I can help with that. So x min, x max. And I'm always aware of what I'm graphing and what I'm looking at. And I see this particular function at least. It looks like x can only be from 0 to infinity, so I'm going to throw an x min there at 0. And in terms of kind of coming outward here, I don't think we have to go out very far. I'm going to go out to 10. I think we could probably do 5 and get away with it, but I'll keep the 10. And that's looking good. Now just be careful. Our outputs here don't represent the y on the function. Remember, you wrote a function for the distance. So everybody, this is the distance in terms of the x-coordinate. So distance here, obviously distance can't be negative, so I'm going to throw in a 0 right there. And these distances look rather small on our coordinate plane, don't they? I can't imagine it's going, beyond a couple units. So I'm going to keep the 10 again. I think 5 would probably be sufficient as well. All right, let's graph. And let's see if it kind of makes sense here. Remember a couple things that I said. First of all, the distance is getting greater and greater as x gets larger and larger. Does everyone see that? So look at the graph. As x gets greater and greater and greater, so does the distance. And then notice what I said is somewhere in here, there's the smallest distance right there. Somewhere right in here, there's a smallest distance. Isn't that kind of cool how that translates? What you think to be the case based on what we see over here bears out in our function. Long story short, there's the minimum right there. Let's go get it. So second, and then trace, so that nice calculate menu. We go to minimum, and I'm going to bring it on in there as best as I can. Probably do this a little faster than me. Come on. So getting smaller, notice getting smaller and smaller. Let's just going to try to keep track of this. Looks like I am to the left of it. So remember, go to the left of it, hit enter, develop a right bound, so anywhere to the right. I'm starting to get bigger there, so it looks like I've got a right bound, and then just hit enter one more time. Now my calculator spits out an input of, as you can see, 0.49, and etc. But that is 0.5, just so you know. And this is our distance right here. So remember, it's x and y, but really what it represents is input and output. Input, output. X value, distance. And so there's your distance right there. Okay, well let's go ahead and get that in. Minimum distance is about 0.866 units from what I saw. So that was the distance. Sounds good. Now notice the last piece, determine the coordinates of the point on the graph that will produce the minimum distance. So if you saw, we got the x value that produced that minimum distance. As I said, that was 0.5. What we're missing, everybody, is the y value on the graph of the function that will produce the minimum distance. So let's look at this visually for just a second. The x value is 0.5, so we're probably looking right in there. That's the smallest distance possible, which was 0.866 units. The question is, what's the y value right there? And of course, if you look carefully, I have an x, and I'm truly looking for a y. I'm hoping you would agree that we can just go ahead and get that piece right there. So y equals the square root of 0.5. This x value and that y value go together. And so grab your calculator if you would. I've got this value in my head, but I'll go ahead and just quickly sketch it out. So square root 0.5 and 0.707. All right, perfect. So the y value that matched that x value is square root of 2 over 2, which is roughly 0.707. Nice. So I'm going to just draw one or two things in here, and then we'll move on to the next. So there's your minimum distance, 0.866. Hopefully you can kind of see that. I know it's getting a little, it's tough to see. Geez, that is hard. But hopefully it'll work for you. So 0.866, that's the smallest distance possible. And then 0.5, 0.707 is that, that point right there that produced the minimum distance. All right, cool. Let's go get example 3. So, example 3, a closed top box with a square base is to be constructed with a fixed volume of 12 cubic feet. Write a function for the surface area of the box in terms of its base width x, then determine the minimum surface area for the box, and then finally determine the dimensions of the box for the minimum surface area. Perfect. So we're going to write a function, of course, and then we're going to optimize. Just again, looks like a minimum problem. All right, well, let's go ahead and see what we need to do. Primary objective, write a function. So let's see, surface area of the box, and that's A in terms of its base width, and that'll be X. So right away, everybody, let's just get that notation in. A in terms of X. Perfect. Now this one, I think a diagram would really be beneficial here. So a little geometry would go a long way in this particular problem. It looks like I have a closed top box with a square base. So this is where my lack of artistic ability catches up with me, but something like that. There's a closed top box, square base, and if you read the problem carefully, and please feel free to pause at any time and read it over a couple times there, but in terms of its square, or the base width, which is X. So it looks like the base is going to be X by X. Now the height, there is no description on the height. So the height of the box obviously is the third dimension, and we're going to call that Y. You can call it H if you want, but I'm going to go X, X, and Y on this, and that seems to be the case. So square base, so that's why those two have to be the same, and in the height, the third dimension, well, a secondary variable has to come in. So this sort of begs the question. If I need to go ahead and write a function for area in terms of X, what is the surface area of this box? I think that's where we want to start. If I have to write a function for the surface area, I might as well at least just see what the surface area of this box is. And if you notice, basically with surface area, it is essentially the sum of the areas of each individual side here. So I've got the top and bottom, areas of those, and then the area of the four sides. It would be wonderful if you could pause for just a second and see if you can come up with the surface area of this box, and then see if you got it right. Let's see if I can pull it off here. So I'm seeing the bottom of the box is X by X. So the area is X squared. Hope everyone sees that. Then the area of the top also has to be X by X, so X squared. So X squared on the bottom, X squared on the top. Again, it's the sum of the areas, so X squared and X squared would be 2X squared. Perfect. Now if you notice, the areas of all four sides are the same, right? They're all essentially rectangles here, X by Y. So if I want the area of the right side, XY. If I want the area of the back, XY, the left, XY, and the front, XY. So I've got four different areas, all XY. If I add them together, well, I can just equate it as 4XY. Perfect. Okay. Notice, area in terms of X is our goal. We have area in terms of X, but also Y. Circle the problem, of course, which is the Y. So here's what we need to do. We need a secondary equation that will allow us to replace that Y right there. And so here's what I want you to do, of course. Read the information carefully and see what else is provided that will allow us to write one more equation over here so we can replace that Y over here. Well, the information that I see, of course, deals with the volume of the box. So one quantity we're trying to optimize happens to be surface area. One quantity is fixed, and in this case it's volume. So in this case, as a constant, the volume of this box has to be 12 cubic feet. And how would we come up with that 12 cubic feet based on the dimensions of this box over here? Well, of course, it is just a rectangular prism, so X by X by Y. And so length, width, and height. In this case, of course, we've got that square base there, so X squared times Y should do. Hope everyone sees that piece. Length times width times height, and we've got X by X by Y. All right. Now this is always the mantra that I repeat with these. So if I need to replace the Y in this equation, I need to solve for Y in the other equation. So we need to get this Y by itself. And I'm hoping you'd be in agreement that we would probably want to divide by X squared. So I'm going to go ahead and do that. These are going to cancel out. And I get Y is equal to 12 over X squared. Excellent. I solved for that variable, so I circle that expression, and I know where it goes. Right in there. So Y is equivalent to 12 over X squared. Now I'm ready to play it out. I have 2X squared, 4 times X, times 12 over the X squared. Theoretically, have I done my job at this point? Area just in terms of X? Absolutely. Only x's on this side. No other variables. I don't know. You can clean this up a variety of ways. I might at least play around with this a little bit. Might make it easy to get in the calculator. So I have a 2x squared, and I have an x over x squared. I hope everyone would be in agreement that this cancels out with one of these. So I'm going to have an x on the bottom, x over x squared. And then just on top, again, this is just multiplication. Remember, multiply fractions just straight across there when you can. 4 times 12, I'm seeing as a 48. So 48 over x. I could probably come up with a common denominator and put those together. I don't know. I don't think that's all that necessary. I'm going to leave it as is. You know, we can, as long as you can get it in the calculator and utilize it according to the problem, you're good to go. All right, this looks great. Area in terms of x. Notice what we want to do in this case. We want to optimize the function. In this case, minimize it. And you can sort of understand the context for this. If we have to get a fixed amount inside this box, so 12 cubic feet inside this box, it would probably benefit us to minimize the amount of materials used to construct such a box. So what would be the best way to construct a box in order to get 12 cubic feet inside? All right, well, let's graph. So go to your y equals if you would. Let's clear that out. And let's type it in, 2x squared. And how about a 48 over the x? Something like that should suffice. And again, guys, just you're going to go to window. You're going to play around with it. See what you can do. Just look at the numbers here. Think about what you see in the problem. I'm going to go 0 to 10 again on the x. So x is the length of the side on the box, and I don't see it being so great here. I don't think it's going to be a huge number by any means. Now remember, the y in this case represents the dependent variable, which remember, of course, it's area. So just make sure you're able to distinguish the variables on the calculator with your problem. So in this case, that's not the y value in this particular function. This represents the area. So area is going to be a little greater. I'm going to go up. I'm going to try 1,000. I don't know if that'll work or not. And if I have to tweak it from there, so be it. Remember, trial and error, everybody. So I'm going to hit graph. And not too bad. Could be better. I think I'm going to bring that down a little, as a matter of fact. Let's get rid of 1, 0. There we go. Not too bad. So again, if you have issues with Windows, just let me know. But anyway, you can see, obviously as x changes, the surface area of the box changes. And there happens to be an optimal way to construct the box. And so let's find out what that would be. I'm going to go second and trace again. Everybody, minimum if you would. Bring that on in. Again, a little harder for me to move on this particular board. Keep it going. Come on. There we go. So I seem to be to the left, so I'm going to hit enter. I'm going to go to the right of it. Again, there's a min somewhere in there. Just anywhere to the right should suffice. Enter again, and there we go. So remember, area in terms of the x value. Area of the function in terms of the base width, which is the x. So there's our surface area right there. Let's go ahead and write that in. Okay, so minimum surface area is, and what did I see there, about 31.45. And I think we are in feet in this case, so let's go square feet on that. That looks good. Perfect. And the x value that produced it was, I think I saw it as about 2.29. I won't bring it up. I think I've got that. So remember that x value represents this dimension right there. So this is about 2.29 feet. This is about 2.29 feet. But this is the unknown right here. So it looks like this was the output, 31.45. The input that produced it was 2.29, and that represents the length and the width. So 2.29 feet by 2.29 feet. Excellent. There's only one thing missing, everybody. What's the height of the box? So you're always looking at your paper there. You're thinking, if I have x, is there a way to come up with the y value right there? So look at that for just a second. Tell me what you see. I'm seeing this piece. I'm hoping you do as well. That the 12 over the x squared should give us that y value. So always keep an eye on the relationships that you've developed in the problem, and then hopefully you'll start to see a calculation that you can do. So I see that 12 divided by 2.29 squared. And again, I rounded here, everybody, so we end up getting something very close to that. And I believe that if this was perfectly done, it should be a perfect cube. So if that seems obvious, well, in this case, that is how it plays out. But there are different variations of this problem, and as a matter of fact, you're going to see those variations where it is not a perfect cube that produces the optimal surface area. So just be careful on that. Make sure you play the information all the way through. Awesome. Let's go do the last one. Example 4. You have 140 yards of fencing to enclose a rectangular garden. Express the area of the garden A as a function of one of the rectangle's dimensions x. Then determine the maximum area of the garden, and then determine the dimensions that will produce the maximum area. Perfect. So we're going to optimize again, everybody. There, in this case, we're going to maximize as opposed to minimize. And let's highlight what needs to be highlighted. Express the area of the garden, which will be A, as a function of one of the rectangle's dimensions, which is going to be x. So, I don't know, even before I draw something, let's just at least get the notation out there. A in terms of x. Perfect. And now I just see we've got a rectangular garden. Okay, not bad. So just draw a rectangle, everyone. One of the rectangle's dimensions has to be x, so it doesn't really matter which you call x and which you call y, which I'm going to do here. I'm going to go x by y. Theoretically, you can go L and W for length and width, and it would work out the same, but I'll just stay uniform to the way I've been teaching it. So there we go. We've got a rectangle, x by y, and remember, here's the goal, area in terms of x. So if I need area in terms of x, I think it is to our benefit to at least write anything we can about the area of this rectangle. Well, this one's probably the easiest formula around, just length times width, in this case, x times y. So that was our goal, area in terms of x. Notice what I did. I wrote an equation for area in terms of x, but it has a y in it. So you can see a sort of a pattern with these problems. Does it always work out this way? No. But as you can see, there's some good math when it does. Okay, guys. Well, if we need to replace that y right there, then I need to solve for y in another equation. So let's go back to the problem and see if we can come up with a secondary equation. So we're going to optimize the area. So what's the quantity here that's going to be fixed? In this case, I guess it's the full perimeter around, 140 yards of the fencing. And so the 140 is just what's fenced, one x here, a y, another x, and another y. So it looks like if I played my diagram out correctly, I have two x's that make up part of the fencing, and I have two y's that make up the other part of the fencing. Okay, good. Well, remember, replace that y. You better solve for y in this equation right here. So let's go ahead and solve for y. Subtract 2x from both sides, of course. Divide by 2. Divide everything by 2, as a matter of fact. 140 divided by 2 is 70. 2x divided by 2 is just x. That looks outstanding. There we go. Y is equal to 70 minus x. I'm going to circle it, and it's going right in there. Nice. So I'm going to play this out a little bit below, but area is equal to x. This replaced the y, so x times 70 minus x. That's super. I don't know. We've done our job, right, everybody? Area in terms of just x. I'm going to at least go ahead and distribute that x in. So 70x minus x squared. Is it absolutely necessary? No. But I did it. And actually, quite frankly, I could probably put that in standard form as well, but I'm going to leave it as it is. 70x minus x squared. There you go. Area in terms of only x. Perfect. Our job obviously is to maximize that area. So as x changes, the area changes. And there is an optimal way to construct this rectangle, of course, that will maximize its area. So let's go see what that is. At this stage, hopefully it's starting to click for you. Again, the key, the test, I suppose, will be if you can do some of these on your own. But obviously, I can assist in any way, be it just constructing the function or finding a window, whatever. Okay, well, let's go get them here. This one I think is going to be a tougher window. I'm going to play around with it a little bit. X is this value right here. Again, can't be negative, so I'm going to keep that 0. And I don't know, we only have 140 feet of fencing. I know obviously it's not even going to be close to that, but I saw that at 140. I'm just going to keep it. Does not matter. Just be in the ballpark, get what you need with the graph, and move on. Remember, the output here represents the area. So what we're going to have to do is find out that length times width and what that area would be. I don't know, 100, 1,000. I'm going to start with 1,000 just to see. So I'm going to hit graph, and not too bad. Looks like we have a parabola right here. I do want to maximize it, so I am missing the top of it. I'm missing the max. So I'm going to go on back to our window here. I'll try a couple thousand, see what happens. Here we go. Is it the best window around? No, but it works. Okay, everyone. Nice. Let's go get a maximum right in there. So maximum right in there, number 4. And, geez, it really has been putting me in a terrible position initially. Let's get that going now. Go to the left of it, of course. Hit enter. Move it to the right, of course. Hit enter. Enter one more time, and there we go. Again, this is what my calculator gave me in terms of the x value. Just know that that is 35. So this is area in terms of x. This is the area, the maximum area, I should say, and the x value that produced it. So just be careful about what these things represent. This is area in terms of x. And this is the best area possible because we've got it at the top of our graph. So maximum area, everybody, is that 1225. Let's see what units I'm in here. It looks like yards. So for an area, how about square yards? Perfect. All right. And then the last thing to do, of course, is to go ahead and get the dimensions of this. Remember, the x value that produced that area was 35. So this right here is 35 yards. So the only question that's remaining is what is the other dimension of the rectangle, which would be this right here. And so again, I would just ask you, if you're given an x, is there a way for you to come up with the y value, the other dimension here? And I'm hoping you see this piece right here. Y is equal to 70 minus x. So in this case, 70 minus 35 would do it. And shouldn't come as a great surprise that we've got a y value of 35 yards. So it's a perfect square. That will, oops, don't need the square on that, sorry. There we go. So a perfect square that produces the maximum area. Out of the infinite number of ways to construct this rectangle, this is the way you would construct it in order to maximize the area. Super. Now, just so you know, you're going to try some of these problems on your own, and there is a variation, well, several variations of this type of problem. They get quite a bit more complex. So don't just always go, oh, it's a square. That's the way I'm going to do it, and then that's going to be the best area. Unfortunately not. So please play out the mathematics in a very similar way to this. Use this as a guide because it will not always work out this way, not by any means. All right, 4 good long examples there. Hopefully it's at least a step in the right direction for you. Let me know if you have any questions on these, of course. And thanks for listening.